so thank you for joining us this afternoon. I'm Bill Fischofer, the Linaro Networking Group, and this is the ODP project update. For those who are not familiar with Open Data Plane, what we are doing with this project is creating an open source and open contribution framework for portable high-performance data plane applications. The concept behind it is to have a common set of APIs to provide application portability, and yet to have also support optimized implementations of these APIs to provide accelerated performance on multiple platforms. And the net result is to offer portability without sacrificing performance across a wide range of architectures. Currently we have ODP running across ARM, MIPS, PowerPC, and x86. And the idea is to allow applications to best match to their price performance needs. But what does this mean in in practical terms? If we look at the big picture of what ODP is trying to accomplish, there's really two perspectives that you can take. One is the application view, which is I'm an application writer. I want to write a data plane application, some sort of switching function, a routing function, other type of operation on packets that really is concerned with performance. And the other is I'm an SoC vendor and I want to support a large set of applications that are potentially able to use my platform. So from an application view, the idea is by writing to the ODP APIs, I get the ability to run on any platform, okay, without at just the cost of a recompile. And on each of those platforms, I transparently take advantage of whatever hardware acceleration capabilities there are on that platform. From a get up here. From a SoC vendor standpoint, the notion is if I support the ODP APIs, then I can compete for any socket, because I will have a rich set of applications that are written to these APIs, and when I sell my value proposition, I don't have to sell twice by saying, oh, I have these virtues, and oh, by the way, they're so good that you should rewrite your applications to run on them. So the organization behind ODP is the Linaro Networking Group. So LNG and its members are the ODP maintainers and its upstream. However, we are open source, open contribution, and everything is done under a BSD license. So those who want to take ODP, modify it for whatever purpose they want, commercial or otherwise, are free to do so. The basic architecture that ODP is promoting is having multiple apps, being able to be supported on shared or dedicated cores. We're looking at systems that are multi-core SoCs that can run Linux on at least one core. We're also providing a framework, not an environment, to allow existing apps to add ODP incrementally. So we're basically leveraging existing SDKs. If we look at how ODP relates to existing apps, apps can add ODP functionality on an incremental basis. The idea being that the degree of portability versus customization to a specific platform is really under the application control. The more applications write to the ODP APIs, the more they will take advantage of the portability benefits. However, there's nothing to prevent an application from still exploiting directly the capabilities of that individual platform if they choose. The components that ODP is providing are really twofold. We're divided into an API layer, which is a common set of definitions, build tools, and validation tests. And this is open contribution, with LNG being the maintainer and upstream for this. And then underneath those APIs is multiple implementations targeting different platforms. And each of those is developed and maintained by its sponsoring owner, which is typically the SoC vendor. And these can be either open or closed source at the vendor's option. So that's entirely up to the vendor as to how they want to handle the distribution of that. There are a number of existing implementations of ODP that are currently available. The one that LNG has been primarily delivering with the ODP API definition is one we call Linux Generic. This is an open contribution platform, which is a pure software implementation of the ODP APIs and basically will run on any Linux kernel. So the purpose of this is not so much to be a performance target, that's something you would actually run in production, but to provide a clear illustration of the semantic intent behind all of the ODP API definitions, as well as to provide a convenient starting point for those who wish to bootstrap ODP onto an existing SoC. All you need is a Linux kernel. You can be up and running in an afternoon, and then use that as a basis for providing more customized and accelerated implementations. And as a result, because we're just targeting Linux, this is designed to support any architecture. There is another implementation that LNG is working on, which is called ODP DPDK, and this is also open contribution, and the target here is Intel x86 boxes using DPDK as the software acceleration layer. So rather than writing to DPDK APIs, an ODP application that's running using this implementation is effectively taking advantage of all the DPDK facilities without having to be tied to the specific DPDK APIs. And of course that's targeting the Intel x86 architecture. And there'll be some discussion of this tomorrow, which I'll reference when we talk about upcoming sessions. There's also an experimental implementation that LNG is doing called ODP NetMap. And this is just basically essentially Linux generic, but with I/O done via the NetMap set of extensions. And this platform is currently available on both x86 and ARM. A number of our SoC members within LNG also have implementations. Texas Instruments has the ODP Keystone 2 implementation, which is targeting the TI Keystone 2 SoCs, which is an ARM-based processor. Freescale has their Linux QRIQ implementation, which is PowerPC based implementation targeting the Freescale QRIQ SoCs. And Cavium currently has two implementations, one for their Octeon series of chips, which are MIPS based, and a newer one which is under development for their new Thunder platform, which is ARM v8 based. And additional platforms are available, or implementations are available under development as well for other SoCs. So the idea is we want to have a rich ecosystem of supporting platform implementations. ODP APIs themselves are organized into groups, and we're just summarizing some of the major ones here. Buffers provide fixed size storage areas for application use. Classification is a suite of APIs that are designed to abstract the notion that inbound traffic can be classified, typically in hardware, into according to various rules. There's a set of crypto APIs that are designed to abstract crypto algorithm offload and acceleration for encryption and decryption of packet and buffer data. Events are just a general concept of notification of various items that applications would be used, such as a timeout occurred or a packet arrived, things like that. Packets themselves are the abstraction for the Ethernet frames and their contents and the ability to manipulate those. Packet I/O is the logic is basically how we logically abstract I/O operations for receive and transmit processing. Pools are provided general mechanism for organizing storage. Queues are the channels used to store events and deliver them to various components in the system. The scheduler is the component that is responsible for dispatching events to execution objects. Shared memory synchronizers for providing multiprocessing primitives, threads, which are the units of execution, and timers. So fairly cover the basis of the sort of things that a typical application would need for doing data plane work. The abstract types all are defined as just symbols. So when I am working with an event, the type of that event is ODP event T. Okay, or the type of a packet is ODP packet T. And the actual definition of what those types are is up to the implementation. So are these pointers, are they indices? It's up to the implementation as to how those are actually defined. All the APIs are just done in terms of the abstract classes. And that's important because what ODP is providing with its APIs are functional definitions, not data structures. So we don't basically say, well, what you pass is a structure that looks like this, and it contains these pointers that go off and reference these other structures. That tends to get you to be into very implementation-specific concepts, which are not, both are not portable and also really limit the underlying platform hardware's ability to innovate and provide accelerated implementations of the APIs. Because we just want to say, what is it they want to have to do, and then let the hardware folks figure out clever ways of really making that happen fast. So applications are really just specifying what they want and letting the implementation figure out how to do that. So just to do a walkthrough of an example of how this works, if we take packets, if you think of a packet as an object, it's a set of bytes which represents a frame that would either be received or transmitted. And packets typically have headers, some sort of payload, and possibly some trailer information. So attributes associated with that packet is, well, it has a length. Okay, so we have a API called ODP packet len. You pass it a packet object, you reference the length. There's also the ability to get the start of a packet if you need addressability to it, or to get the address of any given offset within that packet. But packets themselves are not just to be inspected, but they're also to be manipulated. So logically, prepended to a packet is a concept we call headroom, which is essentially room for growth at the head of a packet. And sets of APIs are available to move the headroom, to push additional headers onto a packet, or conversely to pull headers off of a packet. Typically what happens with data plane processing, a packet is received, the individual layer headers are stripped off and processed, and then perhaps some new headers are added to that packet before it's transmitted onto something. So a good example is a decapsulation or for tunneling, or encryption, decryption. Similarly, at the end of a packet, you may be doing things at the end of a packet for trailers or other types of operations. We call that tail room, and there's APIs for pushing and pulling the tail room. So all of these are just operations that are performable on a packet object, and it's expected that different hardware will support manipulation in different ways for these things. So for Linux generic, we obviously just do this all in software, but other platforms may have other ways of doing it. Packets also have some other attributes. So in addition to just being able to look at arbitrary offsets within a packet, packets typically have structure, okay, because they have defined headers. So for instance, you have a layer 2 header associated with a packet, and we provide an API to get that offset or the address of the packet starting at that offset. Similarly for layer 3, layer 4, etc. The idea being that this is information that's common across all packets, so the ODP packet abstraction captures that and provides that as what we call metadata associated with that packet, and then provides access functions to allow applications to deal with that directly. Beyond these offsets, one of the common things that occurs in many platforms is packets actually internally will be segmented for various reasons. And so although the application is looking at packets as a single object, it's aware of the fact that the packet may in fact be segmented. And so when I get the ask for, say, the layer 2 or layer 4 offset of a packet, one of the outputs that comes from that is here is the length of the segment that's available starting at the requested offset that you can address. And if you need to step across it, then there are other APIs which allow you to step across the various segment boundaries that may exist in that packet. So if we see how this works in practice, if we take a look at the packet receive flow, I have a hypothetical SoC here, which has a number of Ethernet ports. Those are abstracted as packet I/O objects, okay, which allow inbound traffic to be received. Inbound traffic is sent through a classifier function, which is provided as part of the ODP API definition on the receive path. And the classifier itself is customized via pattern matching rules, okay, which say I want to be interested in TCP packets, or I want to be interested in UDP packets received on port 23, or whatever. So these are a fairly general set of rules that applications can write that basically describe the structure of the packet they're interested in. And what the classifier is going to do is it's going to take the inbound packet stream and turn it into what we call a class of service, assign that to a packet. And a class of service has two primary attributes. One is where is it going to be stored? So packets can be stored in different storage pools based on various criteria, as well as a queue that the events associated with this packet should be enqueued to as input to the scheduler. So the idea being that packets come in, they're classified effectively into flows based on various rules, and then added to queues which allow for scheduling of those packets throughout the system. Any questions on this? So if we take this further and now look at event scheduling, you now have a set of input queues which store events. These are fed to the scheduler, and individual threads receive events by simply making calls to ODP schedule to request the next event for them. And the scheduler is in turn going to scan the various input queues and provide scale-out processing to the threads to allow, say who is to receive the next piece of work. Threads in turn can invoke various acceleration engines via ODP APIs, such as crypto, for instance. And the implementations will wrapper these engines such that they interact with the rest of the ODP infrastructure. So if I have a hardware crypto block, the ODP implementation on that platform will take an ODP crypto API and translate that into whatever register manipulation or other types of setup that particular piece of hardware needs, and take the output results from that and feed it back in to the ODP scheduler for redispatch back to the requester. Threads similarly can, once they're done with an event, they can add it back to a queue, and again for it to be scheduled. So this is very much what we call a run to completion model. Receive an event, process it, send it down the line to someone else. And if we just complete the picture by looking at the transmit side, we have a group of threads that are transmitting packets that want to go to a set of output Ethernet ports. Well, the output packets go on to queues. Those queues are associated with packet I/O objects, which then are driving the actual transmission. And one of the things included is a loopback interface, so that if you want to reparse that, that can be accomplished. And a typical use for that is for decryption. So I receive an IPsec packet, I decrypt it, and now I want to send it back in, because now that I have it decrypted, I can say, oh, this really was a UDP packet. Before it's decrypted, I typically will not know what it actually is. Now this is basically what ODP 1.0 is doing, but logically there's sort of a missing piece here, and that is what we really want to have is similarly to the RX path, where you had stuff coming off the wire into a classifier. You want stuff going out through a transmit engine, which could be customized via some series of, say, traffic shaping rules, which control the actual transmission of those packets. So this dotted line stuff in the middle is stuff that we'll likely be working on this year. History. This project started in 2013. The early discussions actually started with, the Linaro networking group was actually founded in February 2013, and ODP was one of the initial ideas that was kicked around. The project really didn't get going until the fall of 2013. We put out our first preview release in December of that year. There was then increasingly rapid development throughout 2014, where we had a number of design sprints to cover major areas like classification and crypto. And starting in the fourth quarter of last year, we started having a fairly rapid convergence on, things finally starting to really come together in terms of defining these APIs in a fairly concise manner, so that we could actually start rolling those out. And what we've seen is we've been averaging a release every week to 10 days now for the last few months. Here's the most recent ones: version 8, 0.8, 0.9, 0.10. 0.11 was actually just cut last Friday, I believe. So that's we're now expecting ODP 1.0, which is intended to be a functionally complete version, which is suitable for evaluation and application development, to be released next month. So that's our current target. And then the idea is, once we've achieved that milestone, we'll focus on the work that needs to be done to take that to the next level, which is having something which is suitable for production application deployment. And the target for that is end of this year. So hopefully by the end of 2015, we will have a more of a battle-tested version of ODP, where a number of our members are working on production-grade applications to test out and make sure that these APIs are solid enough for that use. And that's feedback is what we'll be getting this year, so as we continue to refine ODP. Testing and validation. One of the challenges with a project like ODP is where we have an API which is implemented by many different platforms. Well, how do you know that vendor X and vendor Y are actually implementing the same APIs, or that the APIs behave the same even if they have the same name? And so one of the components of the ODP deliverable is actual set of validation suite tests, which verifies that the API is perform results that is defined by them. And so the intent here is that when someone wants to create an ODP implementation, they have a set of specification, they have a set of reference implementations, and they have a set of validation tests where they can be confident that their platform now implements those APIs because they can run the test and it says pass-fail for these tests. Okay, and right now, I don't know how many total tests there are, Mike. It's several dozen at this point, right?
Yeah, we've basically got a sweep per major API area.
Right. And I think there's probably, you know, a couple of hundred different asserts within all of those, but there's a large number and growing. Right now, for ODP 1.0, the tests are basically what we call sunny day tests, which is correct parameters passed in, you get the expected results. One of the things that we'll be doing over the course of this year is making that a little more robust with, you know, more evil tests that are trying to trick an API into doing something that it shouldn't do, or probing what sort of undefined behaviors different implementations may have, as well as providing more stress tests on those. So how to get involved in the project. We do have a website, opendataplane.org. We also have a mailing list which is very active. So that's again, you can simply go, and from the website you can subscribe to the mailing list. We also have a weekly ODP project call, which is open to anyone. It is held on Tuesdays at 1500 UTC, which is not a particularly convenient time for this time zone. The next call will be on Tuesday the 24th, since tomorrow we're at Connect, and a week from tomorrow people are still returning and recovering from Connect. So we'll have our next call on the 24th. And we do this through Uber Conference, so the URL is you just go to uberconference.com/opendataplane, and you can connect directly from your computer. There's also dial-in numbers if you want to connect via phone, but all the details of that are on the website. And of course, the other thing, like any open source project, we welcome people to contribute code, tests, documents, bug reports, whatever. There are a number of other sessions of interest at Connect, which I would recommend. Tomorrow there'll be a user experience roundtable where a number of the people who've been working with ODP on the implementation side as well as the application writing side will discuss their experiences. On Wednesday we've got a very interesting session comparing Open vSwitch on ODP and it's characterizing its performance. Some other ones then are not ODP specific, but they're very relevant to what we're doing with ODP. There's a session on RT and core isolation, as well as the work that's been done as part of the project for helping to automatically configure tests for multi-node processing, which is obviously in networking without several machines, the tests tend to be fairly simple. So to get more sophisticated tests, you need to be able to coordinate multiple machines and nodes and ports. There's also on Thursday, continuing the LNG tradition, we're having a series of demos. Again, one on Open vSwitch benchmarking. There's also a session which will be talking about the performance and overhead of full isolation, the core isolation capabilities that have been developed under LNG, and also a very interesting talk on using ODP to accelerate crypto using GPU. So that looking forward to hearing about that too. So again, for more information, opendataplane.org is sort of the main portal for all things ODP. And I really want to thank you for coming here, and any questions?
Any preview on what's performance or what needs work?
That'll be covered in the OVS talk to a certain degree. We have not been focused on performance to date from a development standpoint, because we've been really focused on just getting the APIs right. The performance characteristics of ODP are really twofold. One is the efficiency of the APIs themselves, so they actually capture what the application is trying to do. And the second metric that we use is how well can they be implemented across the various SOCs that are implementing them. So in that case, their metric is, how does an ODP application perform relative to someone who is coding to the native SDK for that SOC. And I don't know if anyone has anything that they would care to share about experiences there, but I mean that's something we'll maybe talk a little bit tomorrow at the user experience session.
Thanks.
Okay. Anything else? Very quiet. People are all jet lagged. I don't know about you. It's 2 a.m. for me.
Okay, I've got a second one.
Yeah.
Are there any offloads that you're not targeting, like you think, this isn't a good match?
No, I don't think we've ruled out anything. It's really a question of prioritizing the ones that are interested. I mean, the ones that have, this is where the LNG membership really has contributed in, because we're essentially tackling things in the order which our members are most interested in. So, for instance, crypto offload was a high priority item for last year, as well as classification. This year, we're looking at completing that with doing the traffic shaping on transmit, for instance, and other things are potentially open, like deep packet inspection. A number of SOCs have accelerated facilities for that, as well as other capabilities. But over time, what we'd like to see is, if there is clear application use and need for this, and there are SOC facilities for doing that, we would like to capture those APIs in a portable manner so that they can be made available under that framework.
Great, thanks.
So did you have any in particular that you're, one of your favorites?
Oh, I wonder, will we be able to effectively use regular expression accelerators?
Mm-hmm. Yeah, I mean that's a perfect example of something which is saying, and of course, as an open source project, if somebody says, I've got a great idea for how to do regular expression acceleration, here's a proposal, that's exactly what open source is all about. Even better if here's some code.
I have a question. I noticed you have a project about the ODP and DPDK. I wonder what's the relationship between the ODP and the DPDK. Do you think DPDK is just one SDK implementation of ODP?
Well, that is our intent, is to use DPDK as an acceleration layer for targeting x86 platforms, which is clearly its major focus area. I mean, DPDK has been ported to a number of different architectures, but DPDK is more than just an alternative. It really is looking at a specific model of data plane computing where you have a small number of large cores talking to NICs, okay, for doing I/O, and exposing a lot of NIC-specific structures for I/O buffer rings and things of that nature, which don't necessarily have analogs on SOCs that may not use NICs. They may have integrated I/O facilities where to get a packet you just simply read a register. So ODP is attempting to provide a higher level of abstraction, which can be implemented in many different ways, and one of the now obvious ways of implementing that is to use DPDK itself as an accelerator for x86 platforms. So that's one of the work items that we expect to be featuring prominently this year, is showing that if you write an ODP application, when you run on x86, it's just as fast as if you wrote it natively DPDK. And then you still get the portability benefit of that application can now run anywhere else as well, with accelerated performance on each platform that it's running on.
I have one question.
Yeah.
You mentioned that ODP also supports crypto. So as we know, Linux also support both user space and kernel space, like crypto APIs. So what's the layer between them, like between the Linux standard API and ODP API?
So the goal on ODP is to essentially disintermediate the kernel as much as possible, so that especially if in the data plane you want to get as close to the hardware as possible. So this is one of the reasons for initiatives like core isolation, so that you really want the application to have direct access to the hardware as much as possible. So in Linux generic, okay, which is the reference thing, the ODP crypto APIs simply use OpenSSL, okay, which does the job, but obviously is not the best performing. Whereas on other SoC implementations which have native cryptos, those calls are translated directly into the corresponding SDK calls on those platforms, which allowing for direct hardware access.
Okay, thank you.
So, and that's sort of the model that we're following across all of the APIs. So for instance, if you have a hardware buffer manager, okay, the ODP API calls for buffer management would go directly to whatever the underlying hardware is, whereas in a software implementation, well, we do a software implementation of those. But from an application perspective, it doesn't have to worry about that. It just simply says, hey, here's a set of APIs, and I know that whatever platform I'm running on, I'll get the best performance that I can. But that's a good question. Any others? Still have a few minutes.
Can you speak to how ODP interacts with virtualization or containers?
That's another topic that we were just discussing that this morning. Is fact, it's all part of the productization and production grade readiness for ODP. So that, I mean, right now you can run applications in virtual machines. We have not characterized their performance or what areas of para-virtualization or other things might be necessary for that. So that we expect to be work items for this year to ensure that we can get the best performance in both virtual as well as real environments. So our priorities were basically to get the basics down and then work on filling in the gaps in moving to from real implementations to virtual implementations. Because the other thing is a number of the SoC platforms approach virtualization in different ways as well. So we want to make sure that all of those are well accounted for.
So about parameterization, you already have the plan, or it's just on the to-do list?
These are to-do lists of things that need to be investigated. Okay, so we've, as I said, we have a weekly design call, an open design call, and as these topics come up, we typically use that call to discuss proposed areas of design for the project. And that's where we get the most benefit from different perspectives from people who can provide input to that.
So the APIs themselves shouldn't require any changes.
That's correct. Yeah, however, what I would expect that we would get is maybe we have some, best practices, recommendations for implementations. And, there are obvious things like, well, in a virtual environment, you probably don't want a busy wait. Whereas in a real environment, who cares? You're the only one there. Anything else? All right, well, thank you. It's been a long day, but a productive one. So,